This is Unit 1, Video 1 of Honors Chemistry. This is Part A of the notes. There will be a Part B, which focuses on electronic structure. But the whole unit is over atomic structure. So we will talk about the atom and the different parts of the atom and do some calculations and talk about some experiments that led to the discovery of the atom. So first thing, let's define what is an atom. Now historically, the way the atom was imagined or thought of is essentially like this. Think of a piece of metal, a big chunk of metal, say this is magnesium metal, and then break it in half. And then take the resultant half and break it in half again. Take that half and break it in half again. And keep breaking it in half. And the question is, can you keep breaking it in half forever, indefinitely? And the answer is no. You'll get to a certain point where you can no longer break it in half. And that point is called an atom. So right before that point, you'll get to two atoms, and you split those two atoms apart from each other, and you've come to the base, to the atom. Historically, the word atom, or rather in the Greek, in the original Greek, atomos, actually means indivisible. And we have words in the English language where the A, the prefix A, means it negates the word. So like, think of moral and amoral, or theist and atheist. It means the opposite. So that's what this means, not divisible, indivisible. And that's how historically the atom was thought of. It's really, really tiny particle that you can no longer divide. Now, today, the definition that we'll give is an atom is the smallest unit of an element that maintains the properties of that element. So we have to mention the word element because technically an atom could be subdivided further, it could be split, but you no longer get that same element. You actually turn it into a different element. And so this is kind of the modern definition. Here we have a picture of the atom. We have the electrons whirling around. This is a really big nucleus. This is not to scale. The nucleus is not this big, as we'll see. It's much, much tinier. But this is the general conception of what an atom looks like. So let's define an element, because an atom's definition is connected to an element's definition. An element is a pure substance, which means you cannot break it down further, made of only one kind of atom. So notice the definition for the element contains the word atom in it, and the definition of an atom contains the word element. So this is linked inseparably to an element. So here we have a big flask of the element chlorine, element number 17. Here we have bromine, which is a liquid, it's a red liquid, element 35, and here we have sulfur, element 16, for your visual pleasure. So all these elements, for example, if you take a look in here, you have only one kind of atom inside of here. Each of these elements, you only have one kind of atom, as opposed to if you had a compound, say if you had salt, table salt, that would have more than one kind of atom, which means it can be broken down further. But elements contain only one kind of atom. Now let's talk about the subatomic particles, the parts of an atom. There are three, as everyone knows. Firstly, the electron. It's a very tiny particle which is orbiting the nucleus. Now we have orbiting in quotation marks because, as we'll see, it's not really orbiting in the clean sense like we think of Earth orbiting the sun. That is not the picture. The real picture is quite a bit different. And the mass, it does have a mass because it's matter. Mass is really tiny, 9.11 times 10 to the negative 28 grams. That is a tiny number. And very importantly, it has a negative charge. So subatomic particles actually have charge, as opposed to big items like tables and desks and chairs. Those don't have charge. But tiny particles, atoms for example, can have a charge, as we'll see. The nucleus, which contains the next two particles, is a very dense region of the atom, and it houses the proton and the neutron. So this is a little bit better representation of what an atom would really look like. You have the electron cloud, and you don't see any separate electrons orbiting around. The electron can actually zoom around essentially in many different portions of the atom. It is restricted to certain energy levels, as we'll see, but the electron zooms around here. And then inside the nucleus, we have the other two particles, the proton and the neutron. And so it's extremely dense, as we'll see. The proton has a mass of 1.67 times 10 to the negative 24th grams, and it has a positive charge. So really important to understand that proton, think P as positive. Proton or positive. Think positive like a proton. And then the neutron is the other particle. Notice the same mass. To three significant figures, they have the same mass. If you work it out a little more, you'll see a neutron is a little heavier, but 3 sig figs for us is good, and the same mass. And it has a charge of 0. It has a 0 charge. And so each of these particles not only has a mass, but also has a charge. Now, a very important experiment historically that was performed to discover the real nature of matter and atoms is the gold foil experiment. And this was done by Ernest Rutherford, or Erners Rutherford. His name sometimes is spelled a little differently. But what he did, so essentially he discovered that the nucleus was extremely dense. Historically, the matter was thought of atoms, but scientists thought atoms were kind of dispersed throughout matter in more or less an even fashion. But this experiment actually showed that this is really not the perfect view of it. So what Ernest did is he took a thin gold foil and bombarded it, or shot a bunch of alpha particles at it. Now, alpha particles are actually positive particles, and they actually are helium nuclei. Helium nucleus. That's what an alpha particle is. And what he found is that most of the particles went right through the gold foil, and only a very few of them got deflected, which means most of the matter, most of the gold foil actually is electron clouds, and very, very thin points contain the nucleus. Here is a picture of his actual experiment. So notice that this is the beam of light that was shot at the gold foil, and most, like 99% of the particles went right through. It's as if the gold foil wasn't there. Now the reason they did that is because this gold foil contains electron clouds, huge electron clouds, and these positive particles flying out don't get stopped by the electron clouds, because these alpha particles actually do not have an electron cloud. That's an important thing to understand. So they went right through. And those that got deflected, which were just a tiny percentage, hit essentially the nucleus. So what this told us is that the nucleus is really, really, really tiny, and then really, really dense, because as we'll see, most of the mass of the atom is contained in the nucleus. In fact, from this, we can confidently say a very strange idea, and we can say that matter is mostly empty space. This is a really interesting idea which we'll just explore further. Now, the device used to discover the electron was called the cathode ray tube. This is an important one, and called a CRT sometimes. And what they did is they took a tube and evacuated it, removed most of the air from it, and then they connected to some electricity to here, and they coated the tube with a special detecting material, phosphorescent material, or fluorescent rather, not phosphorescent, fluorescent material. And what happened is we saw a ray come through. Now, they evacuated the air from here so no air particles can get in the way, essentially, of the electrons flying through. And you can actually see this. You can't see electrons just like that. You have to actually have a special coating on here to be able to see it. But this cathode ray tube proved to us that they're actual particles, and we can see them. Electrons can be seen in a way indirectly, and they can actually be deflected by a magnet. A magnet will actually bend the cathode ray up or down, depends how you position it, and the cathode ray tube. Old TVs actually work on this principle. The old TVs, not the flat screens, LCDs these days, but those old TVs with the tube in the back are actually called cathode ray tube TVs. Essentially, same thing happened. You can research a little more about that if you'd like. The relative mass of these three particles are the proton and the neutron are about the same, and we'll give them a relative mass of 1. So relative mass meaning we're trying to even them out in relation to one another, which makes the electron essentially 0 to 3 significant figures. The electron is actually about 2,000 times less massive than a neutron or a proton. So usually when we talk about mass of an atom, we ignore the electron's mass. It's so tiny, it can essentially be ignored to 3 significant figures. Now, a unit used to calculate masses is called the AMU, atomic mass unit. And it's also known as the Dalton. And we'll see Dalton was a very important character in the discovery of an atom and of elements and so forth. And an atomic mass unit is equal to 10 to the negative 24th grams. Now what this means is essentially AMU is used for a really tiny particle like an atom. If I have an atom, what's the mass of an atom? We use AMU. But as you'll see, we'll have to convert it and relate it to grams. So if you have the element lithium, for example, now if you take a look at the periodic table, the element lithium is element number 3, and right below you'll see 6.94. That actually refers to the mass of the lithium atom, and here you can say it is 6.94 AMU. Lithium atom is 6.94, so this could be AMU, atomic mass units. Sometimes also called Daltons in reference to Mr. Dalton, who came up with these ideas early on. So here he is, Mr. Dalton, famous scientist of the 1800s, who actually came up with 4 discoveries, important discoveries. We can call them postulates, like big ideas, and they are the following. Number 1, all matter is made of tiny units called atoms. So let's just say units is made of tiny units called atoms. So this idea of indivisible, he was really one of the ones that brought it back from ancient Greek thought. Atoms are indestructible and indivisible, and that's why we call them atoms. Now, as we'll see, the second postulate is not correct technically today. But if you do destroy an atom, you no longer have that same element, remember. All atoms, number 3, all atoms are of one element are exactly alike, but are different from one element to another. As we'll see, this is also technically not 100% true. We'll discover something called isotopes in the next lesson. And 4, atoms combine in specific ratios to form compounds. This is true, and it'll always be true. So the 2 here that I said aren't exactly true. Just further discovery essentially allowed us to see some other details that Mr. Dalton did not know. So 2 of these laws, or actually 2 of these ideas, correlate to very important laws. The first one is the law of mass conservation. This is a very fundamental law. It's actually the first law of thermodynamics, the first law of thermodynamics, which is a fancy word, dynamics, meaning, like basic science, the first law of basic science, applied in physics, chemistry, biology, any science. And this idea is you cannot create or destroy matter and mass. So an experiment, for example, will be performed. Here you have say one chemical that's down here, another chemical that's in the little test tube, and notice the mass is 300.23 grams. You take the flask, you shake it, you make sure the reaction completely finishes, and then you put it back on the balance, and lo and behold, the mass did not change. So this is true of any experiment. Now, if this were open to the environment, some gases could escape. If you have a gas escape, then it will look like you've lost mass, but in fact, if you catch all the mass of the gas, add it together, the mass would be the same. This is true. Any reaction we perform, mass is not created or destroyed. And the 4th point here is really important as we talk about compounds. Atoms combine in a specific ratio to form compounds. This is called the law of definite proportions. And it says that every sample of a compound contains the same element in exactly the same proportion by mass, no matter where it is in the universe. So salt, for example, sodium chloride, whether it's in the US, whether it's in a different country, on a different planet, in a different galaxy, salt will always be exactly 39.34% sodium and 60.66% chlorine. This is by mass, not by how many particles or something. It's by mass. So if you weigh salt, it actually has more mass from chlorine than it does from sodium. And that's because, as you'll see, chlorine is just heavier. An atom of chlorine is heavier than an atom of sodium. That's really what it comes down to. Okay, so go ahead and try these on your own, and this is practice problem 1, and we'll see you in video 2.